When we studied differentiation, we looked at differentiating products. If we had two functions, u and v, where u and v are both functions of x, we could say the derivative with respect to x of that product uv was given to be v multiplied by du dx plus now u multiplied by dv by dx. We're going to look at rearranging this to help us find integrals of products. So what I'm going to do is rearrange this, and I'm going to have now u dv dx will be equal now to the product here, uv, the derivative with respect to x of that product, which will be d dx of uv, minus now v du dx. So this is the scenario that I can put it into if I wish. I'm now going to integrate both sides of this with respect to x. So the integral of u dv dx will be equal to the integral of d dx of uv, and I'm integrating this with respect to x, minus now the integral of v du dx. Simplifying this term right here, we can say now that the integral of u dv dx with respect to x is given now as the product uv. If I'm integrating the derivative, I'm going to simply have uv minus now the integral of v du dx, and we're integrating that with respect to x. This is what we use to integrate products. This now is called integration by parts. So we've got the integral of u dv dx with respect to x. If you want to just bracket that off and that off, it makes it easier to see, is equal to the product uv minus the integral of v du dx. Now the trick here is to manipulate this. We need to ensure that we can integrate u dv dx. So for this to work, we need to ensure that we can integrate this. What we want is this integral to be as easy as possible for us. What we're going to do is look at the order in which we choose u and dv dx. So what I'm going to do is write up here L-A-T-E. This is log. This is algebra. So algebra. This next one is trig. And then finally exponentials. So exponentials. And I'll just write exponents just here. Just put that. Right. Now you often see in here I, which is inverse trig functions. On this course we won't be dealing with them, so I will just leave it at these. Now what we're going to do is look at some products. So we might want, for example, the integral of x sine x with respect to x. This is a product. There is one function, there is the other function. Now if I consider that this is u dv dx, we want to integrate this with respect to x. The way I'm going to promote this is fairly sort of formulaic, but hopefully you'll understand how we're going about it. So what I'm going to do is now choose which one of these is going to be u and which one is going to be dv dx. So I can see now that if I've got the choice, I'm going to do the algebraic expression first. That is x. What I'm going to do here is just put up a little table. Now I'm going to say that the integral of this right here is equal to the product uv minus the integral of v multiplied by du dx with respect to x. When we're doing integration by parts, it really is a case now of keeping on top of your bookwork. So what I'm going to say then is the following. I'm going to say that the u term, that is the one I'm choosing first. That now is the algebraic term. I'm now going to have the dv dx as the trig. So u is equal to x. What I'm now going to do is find du dx. Now if I find du dx, I'm differentiating u with respect to x. The derivative of x with respect to x is 1. Now what I've got here is dv dx. Sin x corresponds to dv dx. So very similar to the product rule, I'm putting this in a table. So what we've got here now is dv dx. That is sin x. I now want v. I want v because I want it to be in part now of my integral. So if I integrate sin x now, I'm integrating dv dx, which will give me v. That's going to give me minus cos x, and be very, very careful. So if dv dx is sin x, v is minus cos x. So what I'm now going to do is simply use integration by parts. And the way I like to think about this is as follows. I'm going to say the integral of x, and then we had sine x. That's my product. If I integrate this with respect to x, what I need here is the product uv. That is those two multiplied, which is going to give me now minus x cos x. What I now do is subtract away the integral of these two multiplied. That is v, that is du dx, and that's what I want here. So I'm now going to subtract away the integral of minus cos x multiplied by 1, and I'm going to integrate that with respect to x. So what I can say now is the integral of x sine x dx will be equal to the product minus x cos x, that is a product uv, plus now the integral of cos x with respect to x. So we know that the integral of cos x is sine x, so we can now say that this will be minus x cos x plus sine x plus a constant of integration. And that now is the integral of my product. So you'll be given this in the formula book. Ideally, if you can just jot it down on a bit of paper and employ it, it's fairly logical and it's fairly straightforward. All you have to do is keep on top of your bookwork. If you don't, it becomes an absolute nightmare, as we'll see as we're going. So that now is an example here. Sometimes we'll have to use integration by parts twice, and again we'll look at that situation when it arises. Let's look at another integral. Let's go for something else. Let's choose a different one. Let's say we've got now the integral of x squared, the natural log of x. We want to integrate this now with respect to x. So if I go back to my late, I've got LATE. So what I want to do is now pick my u term and my dv dx. Remember, this now is the integral of u dv dx. So we want to now pick those terms. We can see that we've got a log, so that is going to be now my u, and then dv dx is going to be now my x squared, as that's algebraic. So that's what we're going to have. So back again, I like to get at my little table just here, and I like to work around this table. Over time, you certainly won't need to, and even at the beginning, you might not like to. So what we've got then is the u term. I've said the u term, which is the one we're picking first, is the log function, the natural log of x. Okay, let's now find the derivative du dx. The derivative of the natural log of x is 1 over x. My dv dx term, which I've just put up here, now is going to be x squared. So I have x squared. If I'm integrating to find v, that will be 1/3 x cubed. So that now gives me the following. So here is my integration by parts. It will be equal to the product uv minus the integral of v du dx. And apologies that my v's and u's are not 100% clear. So we can say now that the integral of x squared, the natural log of x with respect to x, just matching this up, will be the product uv. So that will now be 1/3 x cubed, the natural log of x, minus now the following. And I'm going to write this in one foul swoop. If I multiply these two, and you will need to show this in the exam, that's going to give me 1/3 x squared. If you consider x cubed over x is x squared, I'm going to bring the 1/3 the other side of the integral sign. That's just a constant. So I'm looking now at the integral of x squared dx. So we can say now that this, and I'll just write it just here, will be 1/3 x cubed, the natural log of x. Now if I'm integrating this right here, raise by a power, divide by the new power, and add a constant of integration. So that's going to be minus 1 over 9 x cubed plus a constant. In the exam, show your full working. The integral, if we integrate x squared dx, we're going to have 1/3 x cubed, and you need to show that and show that you're multiplying that by minus 1/3 in this particular case. I'm doing it like so just to save time. Okay, so there we go. That now is the integral. 1/3 x cubed, the natural log of x, minus now 1 over 9 x cubed. And of course you can factor that if you want. You could write this as 1 over 9 x cubed. Then we'd have now 3 the natural log of x minus 1 plus a constant. And if you were asked to factor it, that is one form that it could be written in. Okay, So let's have a look at another one. Let's look at something slightly tastier. Let's say we've got now. Let's go for what should we go for? We'll go for now x squared, and then we'll have e to the 4x. Let's try this one. Okay, so let's go back to late, L-A-T-E. So on this one, I can see that my u term is going to be the algebraic one, which is x squared, and then my dv dx is going to be the exponential. So I'm going to set this up, and we can say the following. And here's my little table. Again, not required, but it might help you out. We're going to have now the u term. So u is going to be now x squared. We've got now du dx. We're differentiating this with respect to x, 2x. dv dx is what I've chosen to be now e to the 4x. I want to integrate this. The integral of e to the 4x, as we hopefully know, is 1 over 4 e to the 4x. Okay, so now let's use this, and I'll write it back out again. The integral of now u dv dx will be equal to the product uv minus the integral of v du dx with respect to x. Should have a dx there, and I'll let you write that if you wish. So what we can say then is the integral of x squared e to the 4x will be equal to the product of these two, which is going to be 1 over 4 x squared e to the 4x, minus now the integral of these two right here. Again, in the exam, show clearly how you're doing this. I'm just going to write minus 1/2 now. We're going to have the integral of x e to the 4x. Now, this needs integration by parts again. Consider I've got yet another product. So by doing this, I've eliminated 1 power of x. So what I'm going to say then is this will be equal to 1 over 4 x squared e to the 4x. And we need to be very careful, minus 1/2, and I'm simply going to sub this in here. So what I'm going to do is put it in here, okay? So up comes table number 2. This is round 2. I'm applying integration by parts twice, and you will need to clearly show this in the exam. So yet again, I'm going to have the u term being the algebraic one. So this is what I'm considering the integral of. So I'm going to have u will be x. The derivative du dx will be 1. Now I've got my dv dx. That, again, is e to the 4x. The integral, now v, is 1 over 4 e to the 4x. So that's what I've got. So we're going to now use integration by parts. It's the product of these two. So I'm doing it again, which is going to be now 1 over 4 x e to the 4x minus now the integral of these two, which is going to be minus 1 over 4 the integral of e to the 4x. I'm not going to write 1 here, but again, if you're pushed in an exam to do that, depending on which to sit in or what they expect, do show that right away. So let's go ahead, let's rewrite this, and we're going to have now 1/4 x squared e to the 4x minus 1/2. Now this part can stay. We're going to have 1 over 4 x e to the 4x. Now I'm going to integrate this right here. The integral of e to the 4x is 1 over 4 e to the x. So this is going to be minus 1 over 16 e to the 4x plus a constant of integration. So I've just gone ahead now and integrated this. So if I tidy this up, if I multiply this out, and you could, I suppose you could say, let me factor it first. If I just multiply it out, 1/4 x squared e to the 4x minus 1 over 8 x e to the 4x plus 1 over 32 e to the 4x plus a constant of integration. So I've used by parts twice. Let's factor this. Let's take 1 out, 1 over 32 e to the 4x out. That's going to leave me now here 8x squared minus 4x plus 1 plus a constant. So that is now factored. If a question asks you to factor it, factor it. If not, you can leave it in this form. That just looks tidier, I think, especially now if you're considering subbing in limits. Okay, so that's another example using integration by parts twice. And as you can see, this is really about keeping it cool and keeping it together. Okay, let's look at another one. Now, yeah, we don't know what the integral of the natural log of x is. So what we'll do the integral of the natural log of x. There's a trick here, okay? It looks like we don't have a product. What I'm actually going to write is that this is going to be 1, and then we're going to have the natural log of x. So let's go back now to our late, and we can see straight away that our u term is going to be now the natural log. So what I'm going to do is have the other term, dv dx, to be algebraic. So what we're going to have is the following. Now I'll put it up just here. We're going to have now u is the log function, natural log of x. Du dx is going to be 1 over x. If I consider the derivative dv dx to be 1, the integral v is going to be x. Just consider that. All I've said is that now dv dx is 1, therefore its integral is x. So what we can say then is the integral of the natural log of x dx will be the product uv, which is going to give me x, the natural log of x, minus the integral of x multiplied by 1 over x, which is just going to give me 1 dx. So we can say now that this will be x, the natural log of x, minus x plus a constant, or if we like, x ln of x minus 1 plus a constant when factored. So in that one, I pulled a subtle trick to manipulate it. So very realistic or likely questions that you may get. Okay, let's finally finish with a bit of a quirk. Let's look at something that's a bit nasty. Let's say we've got now the integral of, let's go for e to the x cos x. So let's now look at what I'd have. I know using my late, logs, algebraic, trigonometric, exponential, then what we've got here is the following. I've got a choice. Now this is going to be, my trig term is going to be the u, the exponential will be dv dx. So let's just remind ourselves now that by parts, the integral now of u dv dx will be equal to the product uv minus the integral of v du dx. And again, they are with respect to x. So let's set this up. I can say now the integral of e to the x cos x will be equal now to, and we're going to have this in our little table like so. You'll see that many times students just get in this awesome spiral right here. Let's go ahead and say that this is u. Now u I'm going to define to be cos x. If we have now du dx, the derivative with respect to x, minus sine x. If I take now my dv dx, we will take that now to be e to the x, and conveniently now the integral is going to be e to the x. Again, it might not always be that nice that you just get e to the x. So what we want then is now the product of these two. So that's my u multiplied by v. So that's e to the x cos x. Then I'm going to subtract away the integral of these two, which is going to be plus. And again, if you're asked to show this exactly, do minus minus. We're going to get now minus the integral of e to the x sine x. And we're integrating that with respect to x. Again, you might ideally, for completeness, put dx here. Right, so what we need to do is employ by parts again. So we've got e to the x cos x plus now, and I'm going to have to do parts again on this. So let's go ahead and do parts. So let's go down here, and this time what we're going to have as u is sine x. Again, it's trigonometric over the exponential. So we're going to have u, that will be sine x. Then we're going to have du dx, and this is going to be cos x. And then we've got now the dv dx, so dv dx we've got now to be e to the x, and then the integral is going to be e to the x. So what I'm going to have then is the product of these two. If I'm integrating this, it's going to be now e to the x sine x, and then we've got now minus the integral now of e to the x cos x dx. Okay, now just consider that this is equal now to the integral of e to the x cos x. What I'm going to do here is not use integration by parts again. If I use integration by parts, I'm just going to go round and round all day. Now consider that this is the integral of e to the x cos x. So is this. I'm going to add this to both sides. So what we're going to have then is 2, the integral of e to the x cos x is going to be equal now to e to the x cos x plus now e to the x sine x. So e to the x sine x. Now, at this stage, all I've done is said, well, that expression is the same as that one, therefore I'm going to add it to the other side. So just doing a bit of rearranging and factoring, I've got e to the x cos x, splitting both sides by 2 will be equal to 1/2, and I can take e to the x out here, e to the x, and then we've got cos x plus sine x. And again, you can see that it's going to be very similar if you do it the other way round when you're integrating e to the x sine x. So that now is a subtle quirk. Would you get that in an exam? Potentially so if you were led to it. But otherwise it would be some way down in the further maths syllabus. But essentially we can see that employing integration by parts isn't just a case of evaluating, sometimes it's a case of spotting and actually rewriting things. So there we go, integration by parts. Let's finish off with evaluating a definite integral. Let's say that we were given a definite integral. Let's say we'll take something quite straightforward to begin with. The integral from 0 to pi by 4. And let's take something nice and easy. Let's go for x. Let's go for x cos x. We'll integrate that between those limits. So hopefully now you're in the pattern of just drawing up this little table. You certainly don't have to, but you'll see over time that it's kind of quite straightforward. So u, that's going to be x. du dx, the derivative, is going to be 1. We've got dv by dx. That's going to be now cos x. The integral of this, which is going to be v, is going to be sine x. So what we end up with now is the following. The integral from 0 to pi by 4 will be now of x cos x dx is going to be equal now to the product of these two. So we've got now x sine x. So x sine x minus now the integral of sine x times by 1 and minus that, and remember we're going from 0 to pi by 4 of sine, let's write that, sine x dx. Okay, so what we're going to have then is the following. We're going to have x sine x, and now the integral of minus sine x is going to give us plus cos x. So we end up with plus cos x, and we will simply now evaluate this. So we've got now on here x sine x plus cos x, and we're interested in this now from 0 to pi by 4. So if we now consider pi by 4, if I plug that in, we're going to get now pi by 4 multiplied by the sine of pi by 4. The sine of pi by 4 is 1 over root 2, or root 2 over 2. Plus now the cosine of pi by 4, which again is going to be 1 over root 2, or root 2 over 2. Now if we subtract away from that, if I evaluate 0, that's going to give me 0 as x is 0, and then the cosine of 0 is going to be 1. Okay, so what have we got here? Let's just rationalise this. In fact, we'll take it out. We'll have, let's take the 1 over root 2 out. 1 over root 2 pi by 4 plus 1 and then minus 1. So whatever you can make of that in terms of making it look a bit pretty, if you want root 2 over 2, that would be perfectly fine. But that now is going to give us the exact value. Remember, exact values are given in terms of pi and in terms of thirds. So all I've done is evaluated. Now I've stuck pi by 4 through, so pi by 4, 1 over root 2 plus 1 over root 2 minus now stuck 0 through, cosine of 0 is 1, and then simply now subtracted that away. So that would be one way it could be written. I'll let you tidy it up. But essentially that is now evaluating a definite integral using integration by parts. So there we go, integration by parts is just a case of getting used to the formulas. You see on the last example I've just kind of blitzed through it a little, but hopefully that's given you some idea on how you can deal with this.